Thank you very much, Alison. Thanks to the organizers. Yeah, this talk is about work that has been done in this group where I work in Paris, which is called SMILE, for stochastic models for the inference of life evolution, which is in Collège de France in the CIRB, Center for Interdisciplinary Research in Biology. So as many do in this room, in the group, what we try to do is to design probabilistic models of evolutionary processes. We try to design models that generate similar patterns as those observed in nature, and models which allow for inference of these processes from real data. And in this talk, I will focus on a kind of application which is quite popular in evolutionary biology now, which might seem a little weird from the mathematical point of view, at least from the statistical point of view, which is to take time-calibrated phylogenies as the raw data. So we ignore the whole process which goes from gene sequence data to the phylogeny, and we think that the raw data, the raw material that we have, is the phylogenetic tree. And we try to infer processes from the knowledge of the phylogeny. So here, I will try to propose models of speciation, which, well, not really in total detail, but producing phylogenetic trees. So we'll see how we do that. We try to produce phylogenetic trees which share common features with real phylogenies. And especially, we want to be able to compute the likelihood of a given tree under one of these models, under any of these models, right? To be able to make likelihood inference or MCMC inference of the parameters of the processes that generated these phylogenies, exactly as Leah showed us this morning. So an example of a feature of observable statistic that evolutionary biologists are used to consider in terms of phylogenetic data is an indicator which is called beta, which measures the balance, the topological balance of the shape of the tree, which is totally independent of the knowledge of the node depths of the tree, and another one which is called gamma, and which measures let's say the relative branch length in this process, which is totally independent of the topology, but only on the node depth of the tree. So the first statistic called beta is inspired by a model by Aldous called the beta splitting model, and the maximum likelihood estimator of this model is this statistic beta. For Yule trees, especially, beta equals 0, and it has been observed many times that so let's say not all trees, but many real trees are imbalanced. They are more imbalanced than Yule trees. And the gamma statistic is a statistic that measures the relative branch length of the tree, in the sense that, so for the Yule tree, gamma equals 0. The Kingman coalescent, which has nodes closer to tips, has a positive gamma, as in this picture here, to the left. But it has been observed that many real trees, not all, but many real trees have nodes closer to the root. And so one of the goals of many, let's say, macroevolutionary biologists these days is to explain these two patterns. Why do we observe negative betas and why do we observe negative gammas? Just an example. So I will start with lineage-based models, where the smallest entity that we consider in our process is the species. Okay, and from the beginning to the end of the talk, I will try to get a finer grained picture of what happens, namely, like take models where the smallest entity is a population and then an individual. So by lineage-based model, I just mean a birth-death model, but that's the common terminology. So here you see that time flows downwards, but that's maybe one of the last times where I do that. So the particles here, the smallest entities, can be individual or species, but so let's think in terms of species. So particles split into two new particles at rate B and die at rate D, and the particles may bear some traits which, well, not entering the details, evolve as branching Markov processes. So here it's just to make some assumptions about the fact that the rates may depend upon all these variables. So now time flows upwards. the rates here, the birth rates and death rates may depend on time t, they may depend on the number n of standing particles. So when they do depend upon this number, we speak of density dependence in population dynamics, and in this context we speak of diversity dependence. It may depend on a non-heritable trait like age, on a heritable trait, and here we will assume that when there is dependence on a trait, we have asymmetric birth in the sense that the mother here keeps her trait, and the process here of the trait evolving through time is not disturbed by the birth here. And we will assume that these trees are oriented in the sense that the daughter always sprouts to the right of the mother. So here now, the last slide where time flows downwards. So here, just like I think that Leah has used this terminology already this morning. A reconstructed tree, the tree that you obtain from the initial tree by removing all lineages that are extinct by some fixed time capital T. Okay. So basically, the raw data that I was speaking about is the reconstructed phylogeny, because we assume we have no knowledge about the trees that are extinct by the present. So the first proposition is that, okay, so we were interested in the law of the topology of these trees generated by these birth-death models, and the first result that we got with Tanja Stadler from ETH Zurich is that the reconstructed trees that are produced by these lineage-based models of diversification have the same topology as Yule trees, always have this same topology in distribution, if and only if B only depends on time and the number of standing particles, and D only depends on time, number of standing particles, and a non-heritable trait. Okay, so the converse is that when you know that B and D only depend on well, the way it is useful to think about this statement is that when you know that B and D only depend on these variables, you know that your reconstructed tree will always have the same topology in distribution as a Yule tree. So if you do this kind of assumption, your estimate of beta will, of course, not be equal to 0. So the idea is that you take some tree and you compute this statistic. If this tree has been produced by such a process, we will find a beta which is close to 0. Okay, so these processes cannot explain the shape of real trees, at least those that have negative beta. And a second statement is about the whole likelihood, the whole distribution of the tree, not only on the topology, but on the whole tree, the time-calibrated tree or the time-embedded tree, which says that the likelihood of these reconstructed trees always have an explicit product form if and only if B depends only on time and D depends only on time and age. And these trees are called coalescent point processes. Exactly these coalescent point processes that Leah and David Aldos have introduced 10 years ago now. And so I just want to say a few words because they are a very convenient tool that might interest you. So the idea is that a coalescent point process is an oriented tree whose node depths, H1, H2, etc., form a sequence of IID random variables killed at its first value larger than T. So it's a very convenient tool also in terms of simulation, because you just have to draw a sequence of IID random variables, all these HIs, and you stop your process at the first H, which is larger than T. And from this sequence of IID random variables, you construct your tree exactly as Leah showed this morning by reporting here the tip of every edge to the closest edge on its left. Okay? So you draw all these random variables, and then you draw all these horizontal edges that have no reason to actually be dashed lines. They are not dashed lines, they are really the lines that indicate the genealogy here. And you have what is called the coalescent point process. So the coalescent point process is uniquely characterized by the common distribution of these node depths. Okay? And as I was saying previously, the theorem is the following. Maybe let's forget about the details, but the idea is that if you start with a birth-death model where B only depends on time and D only depends on time and a non-heritable trait, let's think about the age, okay? Which actually does only mean that the distribution of the duration of the lifetime of a particle, of a species, is not exponential, okay? It can be general. And if you call GTS the density at time S of the extinction time of a species born at time T, so that might be anything, it doesn't have to be exponential. Then we have this, this nice result which tells you that the reconstructed tree, which is sorry, which is associated with your initial birth-death model, it means that you simulate your birth-death model in forward time, and then you throw away all the dead trees by the present, and you get a tree which has the same distribution as a coalescent point process, with some distribution here h of node depth. Recall that all these node depths have the same distribution, which can be expressed in terms of the ingredients of the model, in terms of this linear integral differential equation. So this means that it's very easy to compute this f by numerical computation of the solution of this equation. And actually, in some special cases where you don't have any time dependence, here you get some convolution equation, and you can solve this equation just by identifying Laplace transforms and inverting Laplace transforms. Actually, this statement still holds when there are mass extinction events or missing species. So this is the kind of tree that you get when you add a mass extinction event. So assume that you start with a reconstructed tree, and that at some time, capital T minus S, you throw bullets. So it's called the field of bullets model. You throw bullets at this at this time here on every edge independently with the same probability. Okay, and this bullet means end of this lineage and of the descending subtree. Okay, so it's called the field of bullets model. It's a model for mass extinctions, and it's used in conservation. Sorry, and it's also used in phylogenetics as a model for real phylogenies, where we know that there are species that are missing from the subset of species. Okay, so when we know that we have a certain fraction x of species that are missing from the subset, we can model the phylogenetic tree by assuming here that s equals 0, and putting bullets here at present time. Okay, and so the previous this statement is also valid for another f, let's say, when there are mass extinction events or missing species. So one thing we did with Tanya Stadler and Helen Alexander here is to apply this result to the recent bird phylogeny that appeared last year. And what we did is to assume that, okay, we don't have time dependence, but we only have age dependence. Okay, so we assume that we have a constant speciation rate, and we assume that the lifetime distribution of species are not exponential. And we decided to parameterize this distribution by a gamma random variable with mean m and shape parameter k. So when k equals 1, we have age-independent extinction rate. So we did tests on simulations to see if when we simulate birth-death models, which are not Markovian, which have gamma distributed random lifetime, can we recover, thanks to our formula, can we recover B and M from our reconstructed trees. And that's what we did. It gives quite accurate estimates when we do maximum likelihood using the previous formula. But of course, it gives good estimates only when we have like 100 or 1,000 trees. Okay, so when you have one single tree, of course you can question the efficiency of the method because you can use maximum likelihood inference on one single object. But that's what they do. We did that for the bird phylogeny, and we rejected strongly the exponential model, meaning that under this model, the shape parameter is actually estimated to be much larger than 1. And what does this mean? It means that the extinction rate of the bird species are supposed to increase with age. Okay, so the hazard rate at which species become extinct is not constant. It increases with age according to this inference. The average lifetime of bird species was computed to be 50 million years, and the speciation rate to be 0.1 per million years. So that was just like a toy, let's say a toy inference on one phylogeny for one class of models where speciation rate is constant and extinction rate is age dependent. And another step that we wanted to take is to devise a model of a phylogeny which is a little more biologically sound. And this is what we did with Rampal Etienne from University of Groningen and Hélène Morlon from INS in Paris. So the idea of protracted speciation is a model that was invented by James Rosindell and Rampal Etienne a couple of years ago. And the idea is here now the particles are not species any longer. They are not individuals yet, but they are populations. Okay, they are populations. So the idea is to take into account the fact that a species is made up of populations. It's not one single panmimetic population, and that these populations may give rise to new populations. Okay. It's also supposed to acknowledge the fact that speciation takes time. So now keep in mind this picture of trees that I showed you previously, thinking that particles are not species, not individuals, but populations. And keeping in mind that any of these lineages is endowed with a trait, a non-heritable trait, which is speciation stage. Okay? So the idea is that each population gradually diverges from the mother species, and the rule is as follows. Newborn populations are called incipient, so assume that we have just two types, okay, just two stages. We can generalize this to any finite number of stages, but assume we have two stages. So the newborn populations are in stage 1, they are incipient, so they represent the same species as the mother population. So you have this cloud of populations for each single species, and they become good after some random time, which is now a new species. You have a new population, which is in the stage good, which is now a new species. But now the difficulty that we have, and that you might have had also, is to define a phylogeny from a genealogy. When you have a genealogy with many individuals or many particles belonging to the same type, the same species, it can be difficult, depending on the model, on the kind of tree that you have. It can be difficult to build the phylogeny from this genealogy. So here what we decided to do with the help of Rampal Etienne, who is the biologist who devised this model initially. So the idea is here that we look at our set of species or set of populations at time capital T. We still have this genealogical tree of populations, and we want to identify each population with the species, and we want to have only one population per species, right, which is representative of the species. So here we have, in this example, 4 extant populations at time capital T. We only have 3 extant species, so the idea is that in dashed line you have the incipient stage. The new population is the incipient stage. and it becomes a good species, a good population, after this random time. Okay? And when it gives birth to new populations, they're bearing the same type, the same allele. They belong to the same species. So at this time, for example, or at this time exactly, you have 3 populations belonging to the same species. This guy gives rise to a new species here. So A, B are 2 new species, and here you have one other species, which is 1. So at this time t, you have 3 species. 1, 2, and 3 are from the same species, and 4 is from another species. And so the idea is, how can we draw a phylogenetic tree from this genealogy of populations? And what we decided to say is that species B is represented by population 4, of course. There's no ambiguity here, but species A could be represented in this set of populations by 2 or 3, and we decided to say that it's 2. Okay, so the first one is this, in this orientation, the leftmost one is the population representing species A. So the phylogeny is clear from that rule. So you have here 1 and 2 coalesce here at this point, and 4 coalesces with 1 and 2 at this point. Okay.
So
and
I'm just a little confused because 2 hasn't become a good species yet, has it? At time t.
Yeah, exactly. So 2 and 3 are incipient species. They're still in the incipient stage. But so if you're in the field, you have these 4 populations, and you know that you can distinguish between these 2 and 1, these 2 and 4. So these 2 are not a new type; they're belonging to the type of the ancestral species here.
2 and 3 are subspecies of the one species, and you're choosing a particular representative in the type.
I think the confusion, 2 and 3 only count because 1 has now qualified.
1 is a new species.
Right.
Yeah, exactly. Yeah. Otherwise, 1 would be the representative of the ancestral species.
But so when you want to draw the tree, then you don't use 3?
Exactly. When you draw the phylogeny, you don't use 3.
Otherwise you don't have monopoly, right?
Exactly. Yeah, exactly. Other questions? Yeah.
So if you're you have some paraphyletic species.
Yeah, exactly.
Going on
Which happens in nature, right? Yeah. Okay. So that's one of the difficulties that we have when we want to define phylogenes. Yeah. So that's a rule. That could be another one, but we chose this one, and on simulations we found that it did not depend much on the definition. But then what we obtain is that actually when the birth rate does not depend on the speciation stage, so new populations emerge at the same rate, only depending on the number of species, on the number of populations, not on their stages. If you do that, you can prove that, so the reconstructed tree, so the one I just showed you with just 1, 2, and 4, not with the population 3, this phylogeny, so the reconstructed tree spanned by extant representative populations, is still a coalescence point process. And the node depth here is given by this formula, which is not very important. The important thing is that we can compute this probability by solving differential equations. And so we did an application on the same phylogeny, the bird phylogeny from last year, but we didn't take the whole phylogeny. We took 46 bird clades, 46 different bird clades. And we did the analysis on these clades. So but first what we did is to test on simulations if we could do maximum likelihood inference on simulated trees to recover the parameters of the model. So the parameters of the model are basically the rate at which you change from incipient to good, the rate at which good species go extinct, the rate at which and the birth rate, the birth rate of population. Okay, so and what we got is that actually the maximum likelihood inference for each individual parameter was not so good. But what was good was the inference of a composite parameter, which is the duration of speciation. So duration of speciation is not the time that an incipient population takes to become a good species, but it's the time before one initial population gets the first descending good population. Okay, so there's a genealogy. There's a genealogy underlying this notion here. And we did quite a good inference of this composite parameter. So we did the inference on these 46 blood clades, and the distribution that we got from these blood clades is this distribution here, where so you see that the duration of speciation goes from it's in million years. So okay, make the calculation. So goes from 10,000 years, okay, to 10 million years. All right. And then what we tried to do with still with Hélène Morlon from Paris is to look at a model where now the particles are not species or populations; they are individuals. And here we really had this problem of defining phylogenies from the genealogies, and so basically in the next two models where we consider genealogies where particles are individuals, so that's where the individual-based population models arrive, and where the lineage-based phylogenies emerge from. So here the definition is that so you have your birth-death tree, for example. So for example, a branching process, and you add Poissonian mutations at rate theta in the infinite allele model, meaning that so it's in both these models the speciation is what's called the point mutation model of speciation, where it's just a single mutation gives rise to a new speciation. And so we tried many definitions of species from this. So new mutations. In the beginning, we wanted new mutations to give rise to new species, and we had the problem of defining the phylogenetic tree from this genealogy. And what Mark, this very brilliant master student, had the idea of doing is to force the phylogeny to be monophyletic, to force the species to be monophyletic, and to identify nodes in the genealogy with nodes in the phylogeny. If you do that, and actually that's the only way of getting monophyletic species, is to identify some nodes of the genealogy with nodes of the phylogeny. Of course, there must be a coherent way of doing that. And what we did is to define species as the minimal monophyletic taxon, such that any two types, so any individuals at present time, with the same allele belong to the same species. So we have the infinite allele model of mutations, and we want to force two individuals with the same type to belong to the same species. Okay? And we take species as the minimal monophyletic such taxon. And we call this model speciation by genetic differentiation. So we did that, and for example here on this picture, so you have mutations in orange here, all the mutation events are in orange, and some of the nodes in the genealogy here are nodes in the phylogeny, but not all, of course. If all were nodes in the phylogeny, this were the phylogeny. This would be the phylogeny. So this is a node in the phylogeny, because here if you take any two pairs of tips whose, let's say, geodesic passes through this point here, they always share, they always have only, at least one allele separating them, so they are in different species. And you do that for any, and there's a let's say, an algorithmic way of deciding if a node is in the phylogeny or not. And so here the problem that we have is that maybe it's kind of a good model for let's say, marking species on the genealogy, but it's more difficult to compute the likelihood of a given phylogeny, because you have to sum up over all subtrees of your genealogy which might be above the nodes of the phylogeny. But what we did is like to represent maybe I won't enter the details here, but to represent the phylogeny in terms of a three-type inhomogeneous branching process. And doing this and using a peeling algorithm, including the case of missing species, so we were able to compute the likelihood of any given tree. And doing a test by simulation, we did very accurate maximum likelihood estimates of theta, this mutation rate, which gives rise to new types and possibly to new species, and B minus D, which is the growth rate of the genealogy. We did that on the cetaceans. So here you have a 2D likelihood plot, B minus D versus theta. So you see that B is smaller than D, is bigger than D, so that you have, maybe I should explain this and skip the last part. So here you see that the maximum likelihood is given for a theta which is such that B minus D is smaller than theta. So it means that your mutations will break up your clonal families into subcritical families. So you will never. So you have B minus D, which is positive. So you have genealogies. So your populations are constantly growing, but they are broken into species so that the phylogeny itself cannot grow indefinitely. And we did also with these parameters that we had inferred from the cetaceans. We did simulations and to see the beta and the gamma statistic, and we got quite good. So for the simulations, we got quite good statistics compared to the real ones. So that's for subclades of the cetacean phylogeny. Just in 5 minutes. Anyway, it's really a work in progress with Guillaume Achaz, Nicolas Lartillot, and Todd Parsons, who is in the audience. Here, the idea is to start with an individual-based multi-type logistic branching process. So again, we have an individual-based model of population. And we assume here that each individual gives birth at rate lambda to an individual belonging to the same species, at rate epsilon k to an individual belonging to a new species, still under the infinitary model. So now really a mutation here gives rise to new species. And you also have density dependence. And this here, this formula says that you have a natural death rate mu. You have intraspecific computation rate C and interspecific computation rate D, and we assume that C is larger than D. Okay, so the intraspecific computation rate is greater than the interspecific. But here only for younger species. So we assume that new species that arises in the metapopulation, a new type, does not feel the competition from all the species present at that time. Okay? And each time a new species arises, it only feels competition, it doesn't feel competition. And so when if a second, sorry, maybe in the next picture it will be clearer. So if you take the large population limit, and you label your species in such a way that species 1 is the youngest, species 2 is the second youngest, then you just get rescaling. Oh, sorry, I didn't get the right date here. Rescaling your abundances. So Xi is the abundance of the ith species. You just get the solution to this system of ODEs, where you see that you have only competition with the younger species. So the idea is that so you start with one species, a second species arises which does not feel the competition from the first species, a third species arises that does not feel the competition from the first two ones, but the second one feels the competition from the new one. Okay, so it's basically a competition matrix which is triangular. Okay. And the equilibrium state of the system of ODEs is geometric. And so, well, so the idea is to, okay, let's forget about that. The idea is to separate timescales. And when you separate timescales, what you get is this picture. Speciation occurs from the species at level I, so the youngest species with this probability, which is proportional to its abundance. And all species at this time simultaneously shift up their level by +1 because the youngest species becomes the second youngest becomes the third youngest, etc. So all the species shift up their level by +1, and the new species occupies the newly vacated bottom level because it's the youngest one. Okay? So you have this, and if you do that backwards in time, what you get is what we call the shift down lookup coalescent, in the sense that all the levels that concentrate shift down their level by -1, except the youngest one, the lowest one, which looks up to a geometrically distributed level and coalesces with the lineage lying there. Have 2 minutes or yeah. So we did like mathematical subtleties to reduce the state space of this process to do a fast simulation, but actually the Markov the transitions of this new Markov process are slower to compute than to do data augmentation on the process. Meaning that if you have a tree, you augment your tree with all the possible labelings at each time, youngest, second youngest, third youngest. You do that, so Nicolas Lartiot did that. And with this, you can compute the inference. So Nicolas has done this MCMC inference algorithm. And what we got is this kind of inference. So alpha, remember that alpha is a degree of, so when alpha is very small, you have one younger species which is really dominant in terms of abundance. So you have very imbalanced trees, and when it's a little more balanced, alpha is inferred to be like a little larger, and when you get very balanced trees, alpha is closer to 1, in the sense that all the species have even abundances, and so there's no species which will give rise or will speciate more rapidly than others. And that's pretty much everything. Thanks to my co-authors, to the members of the SMILE group, and to the institutions. Yeah. Thank you very much.
Very much. Any questions?
I'm afraid to raise my hand.
Please do.
What data about the species do you use to fit the model?
So what we use is like raw just the phylogeny. So we take the phylogeny, we imagine that it's a given, and we compute the likelihood of this given phylogeny, and we do maximum likelihood.
But no characteristics of the species or anything like that?
No, not for the moment. Yeah.
But the timing too. The time information on the trees.
The time information, yeah.
Where do you get the time information?
I didn't get myself the time information, but well, there are molecular clock calibration. There are.
Oh.
Yeah.
So what alternative hypotheses are there for a positive gamma? Or for,
so gamma actually, lots of models can produce gamma. It suffices to have like a time dependence.
yeah.
That, yeah. But for gamma, so the idea is gamma is negative, means that the nodes are closer to the root than to the tips. And what's believed is that there are possible assumptions like creating this pattern is diversity dependence.
Mm-hmm.
So the fact that when there is niche filling, there is slowdown in speciation rate. Others might be time dependence. And protracted speciation is also an alternative hypothesis. So speciation takes time, so there cannot be nodes which are closer to the present.
Okay, this your model also reproduces the observed levels of
Yeah,
negative gamma.
yeah.
and so on.
So all these models, they can reproduce the right gamma. At least let's say protracted speciation, at least this one. Also the speciation by genetic differentiation. So the one with the mutations. But for beta, it's a lot more difficult because as soon as we want to have likelihood which is computable, we are more or less sure to be in the region where the trees are beta equals 0, are actually Yule trees in their shape. So that's why we designed the last one. The last one is a non-exchangeable coalescent model whose topology is really different from the Kingman coalescent or any exchangeable coalescent.
For the protracted speciation model, do you have to assign anything in terms of identifying the taxa as being incipient species or fully fledged species? Or you just give it a list of taxa and then perform the principle?
Okay. So actually we sum over all possibilities.
Okay.
So we don't. But you're right. If we were able to say, okay, this guy is an incipient species, that would add some information and.
I'm asking because, say, like identifying cryptic species is difficult.
Yeah.
And I was wondering if this might be a way that you can infer which possible incipient versus fully fledged species.
Yeah, exactly. So that's something we are working on. Like, let's say, predict the number of cryptic species.
Okay.
Knowing like the phylogeny or the abundance or whatever. Yeah. Exactly. Yeah. But of course, so the next step would be to get more information than just the phylogeny because it's not sufficient.
Well, if not, I suggest we need volunteers to take Amaury for a drink, 'cause it's nearly midnight in France, so it must be cancelled. And can we thank everyone from today for its fantastic time? You're free to go out and play.